Hey there guys, this is Mr. Sheetline. This is going to be the 4.1 notes, check your understandings video. There's 8 of them in here, and I'm going to be walking you through the answers, excuse me, on how to properly get to the right answers. So just like the other time where I'm actually like writing it on a piece of paper, I won't have the questions pulled up. So while you're watching this, make sure you've got your notes out, make sure you've got the questions pulled up, so you can follow along properly with me. I will verbally explain and read out the problems and what they were looking for, but I won't have it written down here in front of you. So again, make sure you have those notes out, make sure you have the check your understandings ready to go. And anyway, let's just get to it. So this is going to be check your understanding number 1. I'm just going to put CU number 1. Okay, so check your understanding number 1. Check your understanding number 1 says that an airport terminal employee is pushing a line of carts at a constant velocity with a horizontal force that has a magnitude of 95 newtons. How much work is done in pushing the cart 16 meters in the direction of the applied force? So we could draw a free body diagram here, and you can if you want. I would actually kind of recommend it. So we've got here an airport employees pushing some carts. So more or less it's just looking like this. Here's a bunch of carts. We'll just say here's a force that's being applied, and it looks like it's 95 newtons. And that's pretty much all we're given. We do know, obviously, that there is some sort of, gravitational force. We know that there's some sort of normal force, and there's probably a friction force, but it's not implied that there is one here. Or I should say they don't explicitly mention it, so I guess we're going to be ignoring it. So here this is about the only thing we have, well, other than the distance as well. So we've got force applied. Force applied is 95 newtons. And we also have displacement. And displacement here is going to be 16 meters. Okay? This one's relatively easy, and it's asking if you're pushing at this constant rate, at this constant force of 95 newtons over the distance of 16 meters, how much work have you done? Okay, so we're trying to find out that work. Let's just write down the equation. It's going to be work is equal to F times D. Okay? Which in this case it would actually look more like F of A times displacement. Okay, so let's just bring that guy over here. So W, and I'm going to plot in the numbers. So 95 times 16. And what we should end up with here is we should end up with 1,520-ish joules of energy. Or in other words, we have 1,520 Newton meters. Okay, and we have our answer. So this one's pretty easy. Okay, pretty easy. Now the next one is still fairly easy, just not as straightforward. So okay, so check your understanding number 2. So check your understanding number 2 says here that a 2,000 Newton force is applied to a cable used to tow a car as seen below for 20 kilometers. How much work is being done? And then make sure that you answer this question in megajoules. Okay, so we're given that there's an applied force acting on this car, on the cable, and it is applying 2,000 newtons worth of force. It is also traveling horizontally. It is traveling 20 kilometers. Okay, so before we move on any further, I'm going to change this real quick. I'm going to change this to meters. So it's going to be 20,000 meters. Okay, because we can't use this. Our number is going to be off if we use kilometers. Remember, it's Newton meters, not Newton kilometers. Okay, and then the other thing, there is a third guy here and a third one here. If you notice that picture, in the picture, which we'll draw a free body diagram for this real quick after I write this. In the picture, we see that theta is going to be equal to 50 degrees, okay? Because here's our car, and then here is that tow cable, okay? And these are all of our forces here. So here's that tow cable, and arguably here, this is where they put the degrees, the angle, I should say. This is where they mark it. But remember, opposite inside or opposite inverse angles are going to be equal. Okay, so 50 here, and then I think, what is that? The law of transverse angles, I think, is that if I'm remembering that correctly. So that guy's 50, so that means that this angle is 50. Okay, so that is how we have a theta of 50 degrees. And then not only that, this is where the force applied is coming from. It's coming from this angle, which is 2,000 newtons. So what we need to find, though, is we need to find the force applied in the x direction. So why do we have to find that? Well, remember, we have to find this guy because we're traveling horizontally. We're not traveling diagonally. So we have to make sure that we find the horizontal force so that we can then apply it to the distance traveled to find out how much work was done. Okay, so we need to find a couple things. So we need to find horizontal force, and then we need to find the work. Okay, so easy peasy. It's a simple triangle here. So 50 degrees in there. We're trying to find FAX, and we have FA. And we're going to use SOHCAHTOA. And we're going to be using this guy right here. So it's going to be the cosine of theta is equal to the adjacent over the hypotenuse. Since FAX is the adjacent, hypotenuse is F of A. It's going to end up looking like this. FAX is equal to the cosine of theta multiplied by the applied force. Okay, shift that up a little bit. So then I'll turn into cosine of 50 multiplied by 2,000. And we will get 1,285.6 newtons. And we'll say it's that like forward. Okay, so we've got our applied force, our horizontal applied force, and then that's what we're going to use with the. We're going to use that and multiply that against the distance traveled to find our work done. So over here, we're going to say work is equal to FAX times displacement. So that's going to be 1,285.6 times 20,000. And then overall, we are going to have an answer here of 25,712,000 joules. Now, because we have to represent this in megajoules, as it says here, 1 megajoule is equal to 1 million joules. Or you can just—it's basically 1 times 10 to the 6th. So we're just going to go here 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. So our final answer, we should just have it as basically 25.7 megajoules, and it's a capital M there. Okay. And then we have our answer for check your understanding number 2. Okay. So let's check out number 3 now. Check your understanding number 3. Okay. So a store clerk moves a 4.4 kilogram box of soap without any acceleration along a shelf by pushing it with a horizontal force with a magnitude of 8.1 newtons. If the employee did 5.9 joules of work on the box, how far did the box move? Okay, so it gives us mass. I have a feeling that we're not going to need this, okay, because there's really no indication. They give us the amount of force here, and they also tell us that, the amount of work that's been done it. Somehow they already know that, so we have to figure out how far this box moves. So I don't really think that this is going to be necessary. It would be kind of necessary if we didn't have the energy, if we didn't have the energy already given to us, the amount of work done, and we were told to find out the amount of force being applied, but we'd also need the we would need the kinetic friction coefficient in order to do anything with this. So we're probably not going to do anything with this guy, but we'll write it down anyway because it's been given. It gives a horizontal force here, so that's our applied force in this case of 8.1 newtons. They tell us the amount of work done is 5.9 joules. and then we've got to find the displacement. How far was this guy pushed? Okay, again, you can draw a free body diagram if you want. This one's pretty straightforward. It's everything it says is horizontal. So for the most part, at least it says horizontal force. So it's implied that the distance traveled is also horizontal. If it wasn't, it would tell us. So it's basically just work is equal to the force applied times the displacement, and we're trying to find this guy, so then it ends up being displacement is equal to work divided by the applied force. So we just plug those in, so 5.9 divided by 8.1, and that will give us here a displacement of 0.73 meters. So about 73 centimeters, this guy, roughly 3/4 of a meter stick is how far we push this box of soap. Okay, or at least the store clerk did. Okay. All right, number 4. Number 4's got a couple of them going on here, but realistically speaking, it's not a terribly difficult question. It's actually quite easy. It's filled with a lot of stuff just to kind of throw you off. Okay, so let's see what it says here. So a toboggan carrying 2 children, which has a total mass of 85 kilograms, reaches its maximum speed at the bottom of a hill, and then glides to a stop in 21 meters along a horizontal surface. The coefficient of kinetic friction between the toboggan and the snowy surface is 0.11. So it's pretty low. So meaning that it's not that we're, frictionless, but it's pretty close. Okay, so A, we have to draw a free body diagram of the toboggan when it's moving on the horizontal surface. Then B, determine the magnitude of kinetic friction acting on the toboggan. And then C, calculate the work done by the kinetic friction. Okay, so looking back, and I didn't write CU. CU number 4. Yay, we're halfway there. Yay. So they give us a total mass here, and the mass is going to be 85 kilograms. Looks like we're probably going to use this because they give us the kinetic friction coefficient. Also, because we don't know what's exactly happening here. We know that kinetic friction is being we're asked to calculate the kinetic friction, but we're getting a little ahead of ourselves here. So maybe we'll just write down what we have and then come back to it. It says that at the horizontal in this, it took them 21 meters in order to come to a full stop, which is pretty far, decently. And let's just say this. Okay, so we know that starts up at the top of the. Actually, I'll just say in my notes I was preparing to have to calculate acceleration, but we may not have to do that here. So let's just hold off. Let's maybe just draw the picture first. So yeah, I'm going to draw a picture first, and then I'm going to draw the free body diagram. So this is what I imagine is happening. So there's like a hill here, and I'm going to put a little dotted line here for a second. So here's the toboggan, and here are the kids that are in the toboggan having fun. Yay, look at them. Okay, then they're going to go down this hill. At some point down this hill, because obviously their initial velocity here is going to be 0 meters per second. And then their final velocity for the most part is going to be right here once it reaches, because that's where they're going to change directions. And then they're more relatively speaking, our horizontal at that point will be technically, it wouldn't be, we'll just say that its final velocity here would be its, or the initial velocity in the horizontal would be its final on this angle, more or less. But anyway, so this is where they start and they go down, and then it reaches a point in which they're at a horizontal. And from here to say here, so from here to here is that displacement of 21 meters till they come to a stop right here. Okay, and we want to know how much friction, how much force of friction, how much work did this friction do over the span of this distance for it to come to a stop. That's what we're trying to find out here. So we're not going to worry about this whole spot. So our free body diagram is going to look like this. Okay, we definitely have mass here. Okay, which then also means that we do have gravitational force, which also means then we do have normal force. Okay, just real quick, just to calculate it, we've got 85 times, it'll just be that quick 85 times 9.8. So that means that we've got 833 newtons, both for the gravitational force and also the normal force. Okay. Now we don't have a force going this way though. Okay, no force going that way. But we do have a force going this way. Okay, and this is going to be that kinetic friction force, and we don't know what that is yet. That's what we've got to solve for. So here is our free body diagram. This is what it should look like. Again, there is no force in this direction. We have motion in this direction, but there's no force in this direction. We have an opposing force of that motion in the form of friction, but again, no pushing force to continue that motion. So there's A. Okay, and now B. We've got to determine the magnitude of kinetic friction. So, oh, and I didn't write up here. I didn't write the coefficient. 0.11. Okay. So 0.11, and I'm going to rewrite it down here actually, 0.11, and now, because I've calculated this, I do have force of gravity, which means I've got normal force. I need to find out what the kinetic friction force is. Okay. And to do that, remember it's the classic friction coefficient equation, where it's going to be the coefficient is equal to the friction force divided by the normal force. So to find this guy, we just have to shove him over here. So then it's F of K is equal to the coefficient times F and normal force. Plug them in. Normal force is 833. And what we should get here is that we should get 91.6 newtons backwards for this answer. Okay, and that's B. Okay, so there's, once they hit the friction, or once they hit the horizontal part of the hill, at the bottom of the hill specifically speaking, there is roughly about 91.6 newtons worth of force acting upon the toboggan. That's going to eventually slow this down to 0 meters per second, make them come to a stop. So now we got to calculate the work being done. So for C, so we've got the friction, the kinetic friction force. We have the distance traveled. Okay, and the distance traveled in this case is 21 meters, and we've got to find the work. Now, the only thing is, remember, the work, and this is where it's getting into that weird kind of positive work, negative work kind of realm. So yes, it is a friction force, but what is the positive? What's the positive direction here? Positive direction arguably is the direction in which the sled is moving. So this friction force here is technically going to be a negative, technically speaking, okay, while we're finding this work, because it's work that's opposing the motion. But if it's work that is helping the motion, it'd be positive. But in this case, we have a negative force here because it's in the opposite direction of the motion. So that means our work is going to be negative. But we're just going to do the old classic normal work equation here. Just in this case, we have a negative number. So it'll be negative 91.6 newtons times 21. And then what we'll have here is negative 1,924 joules worth of work happening here. Okay. And then that would be our answer for C. Okay. But remember, work is a scalar quantity. We don't associate a particular direction. The direction has already been implied, specifically right here in this case, by saying that, oh well, it's a negative direction to the motion, so that means the work being done is in the negative it's in the negative opposite direction of the distance traveled. Okay. All right. Then number 5. Number 5 has a couple as well. So a bag of groceries of a mass that has a mass of 8.1 kilograms is raised vertically without acceleration from the floor to a countertop over a distance of 92 centimeters. We have to determine the force needed to raise the bag without acceleration, and we also have to find the work done on the bag of groceries against the force of gravity. So what it's saying here, and what's happening here, is we're picking up just a bag. And it's asking us exactly what I just read out, is that we have to know, well, how much force do you need, and then how much work was done on this bag. Okay, so let's just write out what's given to us. So mass is going to be equal to 8.1 kilograms, and then our displacement here is going to be a vertical. It'll be a vertical displacement of 92 centimeters, which is actually just going to be 0.92 meters. Because remember, it's not Newton centimeters, it's Newton meters. So we have to make sure we convert these distances, these displacements, from whatever they start off at to meters, if they're not already provided in meters. Okay. So, okay, we've got the mass, we've got the displacement, and now we need to find the force. So we don't know what the force is. Okay. We have no clue what it is. So how do we find it? Well, it says here that this bag is being raised without acceleration. So that means that velocity is constant. And if velocity is constant, that must mean then our net force is 0. Well, technically speaking, our net force is 0. Now, that doesn't necessarily mean, though, that we have. It doesn't necessarily mean, though, that we have. What's the word? That doesn't mean that we don't have work being applied here. So this is going back to in the notes when I mentioned that, it depends upon the question being asked. Where is it that you're wanting to find the work done? Are you wanting to find the work done on the object in order to get it from point A to point B, or is it going to be the work done overall? Okay, in this case, it's asking specifically work done on the bag against the force of gravity. If it were to say what was the amount of work done overall, like what's the net amount of work, it would be 0. Okay, now why would it be 0? Well, what is the minimum amount of force needed in order to move an object in order to move it without acceleration? Well, then that must mean then in this case, our force applied has to be equal to the opposing force, which is going to be the F of G. Okay, because again, velocity is constant. And because velocity is constant, that must mean that our applied force has to be equal to the force due to gravity. So, if this is our bag, force due to gravity here is going to be that 8.1 times 9.8, which is then going to tell us, let's see, I have them on my notes here, which means that it's going to be roughly 79.4 newtons. Okay, so if that's the amount of or gravitational force, then our applied force will be equal to that, just in opposite direction, which will be 79.4 newtons in the opposite direction. Okay, again, it's because it prefaces that it is there's no acceleration; it's constant velocity. Okay. So we now have our applied force. So that's A. So A is answered. So F of A is equal to 79.4 newtons, and then we'll put up. So there's A, and then B. How much work was done in order to do that on the bag? Work is easily just going to be F is equal to F of A times displacement. So 79.4 times 0.92. My marker's starting to run out a little bit, which is going to give us 73 joules, roughly speaking. Let's see, double check that real quick. Yeah, 73 joules worth of energy. And there's number 5. Okay, almost there. And pretty much the rest of them. Number 6 was already given to you on accident. I didn't mean to keep that answer there. I thought I deleted it, but I guess I didn't. But a student pushes against a large maple tree with the force of with the magnitude of 250 newtons. How much work was done on the tree? Well, if you've got your tree here, and you've got a kid that's like, man, you know, putting a force in this direction, but that tree ain't moving. So you have 0, meters traveled. Well, because your distance is 0, so because your displacement is 0, work will also be 0 because you have to use that energy in order to move the object. And if the object doesn't move, you don't have work. Now, does it mean that you're not putting energy into pushing this tree? Of course not. Of course you're using energy in order to try to push this tree. It's just to say that how much work does a student do on the tree? The idea being is that, well, how much energy did you transfer from yourself to the tree? And in this case, realistically speaking, and as far as work is done here, it's 0. But of course, you're expelling energy in order to, tense your muscles, in order to push against the ground, to exert force from your own body and leverage that force into the tree. Of course, that's happening. But because it doesn't move, we can't calculate that kind of work done. Now, you can calculate the work done by arguably the amount of calories you may spend to do that, depending on your metabolism, but that we don't do that here. Okay, so then we've got check your understanding number 7. So a 500 kilogram meteoroid is traveling through space far from any measurable force of gravity. And specifically here, the force is pretty much approaching 0, which means it's nearly 0. If it travels at 10,000 kilometers per hour, for 100 years, how much work is done on the meteoroid? Okay, well, we've got this lovely meteoroid that is moving. Give him a little face. Why not? This little dude is moving through space. And he's moving through space at a velocity of 10,000 kilometers per hour. Wow, that's so fast. That's so cool. How much work is being done? Well, let's see here. Well, we know that its mass is 500 kilograms. And it says here it's traveling through space and it's far from any force of gravity. Well, that means then that there really is no force being applied here, and especially because force is pretty much approaching 0. Well, force is approaching 0, well, that pretty much means that, in this case, force is 0. So if the force is 0, yeah, we may have some distance traveled. Like you could measure out how much distance this guy travels at this rate over 100 years. But there's really no force being applied here. So because our force is 0, our work is 0. Okay? So we need a force in order we need a force, not just distance traveled, in order to calculate work. So in this case, really, arguably speaking, in this specific context, no work is being applied to this meteoroid. Now, wherever this meteoroid began at, once that force was applied, whether it was, let's say that this meteoroid was maybe it was one of the large chunks of ice that was on Saturn's rings that just happened to be on the very outside edge that was slingshot out of orbit, and it just continued to travel. Now, arguably, that really doesn't happen as far as I understand it, but let's just say if it did. Or let's just say it was orbiting another large planet, another large celestial body, and it just continually just kind of circled around, orbited around it, and then eventually just got wider and wider, and eventually just slingshot. And we'll get kind of into that when we get to circular motion. It's actually kind of a fun unit, really. We get to do a lot of stuff with space stuff. It's really cool. But we don't know the force being applied here, and at this instance, because it's pretty much 0, so that means our work, again, is also 0. And then the last one, so check your understanding number 8. I know you've carried on this far. I don't even know how long we've been going. I'm sure it's been about like 25, 30 minutes so far, but we only have this one last guy to cover. So you are walking east at 30 meters per second while holding a box that has a mass of 10 kilograms still on your shoulder. So meaning you're not moving it. Okay, it's sitting still on your shoulder. And you walk 20 meters. How much work is being done on the box? Okay, so let's see what we got here. So we've got velocity, constant velocity at that. Moving east. And you've got this box here that has a mass of 10 kilograms. Okay, it's on your shoulder. And you walk 20 meters. How much work is being done? Well, let's see here. Let's first draw this out and then maybe draw a free body diagram during this whole process. So here you are, okay? You'll also have a nice little smile because you're so happy to be carrying this decently sized crate box, and you got this box on your shoulder. And you are just having so much fun moving this box, and you're going to move in this direction for 20 meters. And we want to know what's the work being done on this box. Okay, well, okay. So here we have context of what's happening. Okay, so from here and then over to here, this is where the box will still be. Okay. Here's where the box will still be. What is the amount of work done here? So let's draw the free body diagram of the box. Well, we do have, we've got two things going on here. We do have a normal force, technically speaking, and we also have gravitational force. And they're pretty much equal. And that's it. So, question, what's the work being done here? Answer, work is 0. Why is it 0? Especially if we've traveled 20 meters. Why 0 if it's given us the speed? Oh my God! And I'm just now realizing this. This is not a walking speed. Oh boy. Sorry. Your dashing speed with this box over the span of this distance, the work is 0. Why is it 0? Because there's no force being applied. Okay. Now your question may be, well, Mr. Sheeline, aren't we producing this normal force on the box? Yes, you are producing that normal force on the box. However, the box is neither moving or accelerating in the x-axis, in the vertical. There is no motion. It is pretty much still. Okay, so if the force is being applied here, in the vertical, but then the distance traveled is on the horizontal, in other words, your theta for the most part is 90 degrees, you have 0 work done. Okay. Now, let's say if you're walking this distance, and then while you're walking this distance, you lift it above your head for like at the distance of half a meter, and you did it at a constant. If you did it at constant velocity, oh yeah, you could definitely 100%. You could calculate the amount of work done in the horizontal. Okay. Or sorry, in the vertical, not the horizontal, in the vertical. Because now you have motion and you have a force in the vertical, and you can find out what the work applied is in the vertical axis. But during this time, you yourself are not moving that box horizontally while you're also walking horizontally. So in this case, work is 0 joules. Okay. Okay, so real quick, just a quick note on this. If you put in cosine of 90, do that for me. If you put in cosine of 90, Put in cosine of 90 in your calculator and tell me what you get. Okay. Well, you don't have, it's a video, so you can't really tell me, but what you should find out is that cosine of 90 is 0. Okay. So easy way to figure that out, easy way to see that. Okay. All that good stuff. All right, guys. Well, that is everything. That is the entire Check Your Understanding. That was a whole bunch of them. So hopefully you're starting or have had a decent idea of what work is. If you have any questions for me, remember my virtual office hours. Okay, virtual office hours on Tuesdays and not through. Tuesdays and Thursdays for you guys for physics. Remember, for physics, you guys are 9 o'clock to 9:40. So I'll post a link every Tuesday and the next 2 or 3 Tuesdays and Thursdays. And then after we come back from break, I'll do that for a week or two. And your guys' time is 9 o'clock, 9 a.m. to 9:40 a.m. So make sure you get a hold of me using the link I provide for you on Google Classroom to talk and chat with me and to ask some pretty good questions. Okay? All right, well, that's the video. So if you still have any questions, get a hold of me. Come to my virtual office hours. If not, I'll see you guys in the next one.